Hello, and a warm welcome to IGCSE Coordinated Science, How to Answer the Chemistry Questions in Paper 4. Table 1 shows some information about three elements A, B and C. Group number 1, number of outer electrons in group 1. Everything in group 1 here, which you all should be familiar with. Clearly, the group number is the number of valence electrons, number of electrons in the outer shell. Group 1, we should all know our sodium, lithium, potassium are highly reactive and they kick you-know-what in water. Element B, group number in periodic table is 7. It's a bit naughty because we've not used that for a while now. 7 is here. Manganese, technetium, rhenium and borium. We know that the IGCSE is a little bit behind the times. It's actually group 17. So fluorine, chlorine, bromine and iodine are all fair game for you on your IGCSE. Number of outer electrons is clearly 7, and it tells me they are reactive. Indeed they are. You don't want to come across some fluorine anytime soon. It is highly toxic. Group number is the same as the number of outer electrons, so that's 8. And clearly group 8 again is wrong. It's group 18. It's helium, neon, argon, krypton, xenon, radon, and organoson. You'll never hear of organoson in an IGCSE. Radon maybe in a physics radioactivity question, but mostly they'll be asking about argon, neon, and helium for your group 18, or as they call it, group 8. And they are noble. They're far too posh to react with the likes of us. D, E, and F show the structures of 3 metals. D, with 2 different metals. We can also deduce from this diagram here that there are 2 different types of metals. How do I know this? Because all these atoms are the same colour and the same size. It's a better way to say they have the same atomic radius. However, these large grey atoms in the bulk here have a different atomic radius or a different size. In this case, they are larger than the white, smaller circles here. So these are 2 different metals in the bulk matrix. E, they're all the same. It looks approximately like the same size as D, but the point is that this is a pure solid. How do I know it's a solid? Because all of the atoms are touching. That's not an alloy, that's a pure metal. F, well, these are discrete, separated molecules. They're probably covalent gases. How do I know that? Because they are different colours. There are no forces attracting them between them. They are free. I assume that they are randomly moving. And this could be fluorine and chlorine or oxygen and nitrogen or any of those. So which is an alloy? Clearly the answer is D. Why is D the answer? Atoms of 2 different sizes would be a good thing to say. Or atomic radius is better, and E is a pure metal, and F is a covalent gas. So these are models of the world around us. That's enough to hit the mark scheme? Yes, it is. More than enough. C, a small piece of sodium reacting with ethanol. It's really quite a nice, cute reaction, this one. Sodium sits at the bottom, gently bubbling away hydrogen gas over time. It's at 25 degrees C. Why do we care? Well, we care because the molar volume of a gas at 25 degrees C is 24 decimeters cubed. It tells me the total volume, that's in here, volume up here, of hydrogen gas is 8.4 cm cubed. Oh, okay, cm cubed. And that the number of moles of hydrogen gas is calculate the number of moles of hydrogen gas. The molar volume of the gas is 24 dm cubed. Now 24 dm cubed is the same as 24,123,000 cm cubed. Okay, because 1 decimeter is 10 to the power 3. So if we times our 24 by 1,000, this means that the units for the molar volume of gas at 25 degrees C are now the same as the units for the experimentally collected hydrogen gas. So now I can do 8.4 over 24,000. It's now the birth in centimetres cubed, which I make 3.5 by 10 to the minus 4. So I always use standard notation in science. That's how scientists communicate, and that's the correct way to do it. They would give you 2 marks for that. If you just did 8.4 over 24 and forgot the units conversion, so you ended up with 0.35, you would have got 1 mark for that. Just so you know. The experiment is repeated. It's a temperature of 10 degrees C, so we've gone down in temperature, a lower temperature. Suggest how reducing the temperature affects the rate. So, lower temperature means lower average kinetic energy of the molecules. They are moving around with much less energy, more slowly. If they are moving more slowly, so slower molecules means less chance of successful, by successful I mean producing products, successful collisions. There we go. So lower temperature, lower average energy, so fewer molecules have sufficient energy to overcome the activation energy barrier, and therefore it's a slower rate of reaction. So I need to say, forgot to say, therefore reaction rate is slower. Don't forget to reread the question. Okay, state is one command term. We've stated lower temperature, lower average kinetic energy means the molecules are moving more slowly, so there's less chance of successful collisions. That's now stated and explained. So that's my explanation. And here is my state. It's asking me, how does the reducing the temperature affect the rate of reaction? If I'd not revisited the question and checked my response, I'd have thrown away 1 easy mark, which we see a lot of when we mark these papers. Biology, physics, that's available on a separate video. Now, question 4. The ionic half equation when zinc or atoms form zinc ions is shown below. Write an ionic half equation for a metal that is more reactive than zinc. Well, anything that is more reactive than zinc, I don't know, let's try magnesium. So Mg going to Mg2 plus, you could use, I don't know, sodium, potassium, lithium. Give me a, there we go, 2D minus, and just need to make that a superscript. Mg2 plus 2 electrons. Does it require me to make state symbols? It doesn't. But again, any reactive metal here, more reactive than zinc, you will get this reaction. If you're using sodium, don't forget, or lithium or potassium, don't forget it's 1 electron, not 2 electrons, for that oxidation. Oxidation is loss of electrons, right-hand side. When zinc is added to aqueous lead, a black deposit of lead is found. The ionic half equation is here, so zinc is going to zinc 2 plus, and we also have zinc is going to zinc 2 plus, lead 2 plus is going to lead, so lead picks up 2 electrons to become lead, solid, so that's a reduction because it's gaining electrons. And zinc is going to zinc 2 plus, plus 2 electrons. Those 2 electrons from the zinc being picked up by the lead are the same 2 electrons. Write an ionic half equation for the reaction between aqueous copper nitrate and zinc. Now, copper nitrate is Cu2 plus. So I want the ionic half equation. I don't care about the nitrates, the ionic half equation. So Cu2 plus, and we need to make that a superscript. And we need to add that 2 zinc. Oh, it's zinc. So zinc is going to be more reactive, Z. And if we can do that one, yes, we can. And we're going to make our Zn2 plus Cu. Don't forget copper. If it ever asks you the colour for copper, the answer is copper colour. So Cu2 plus Zn goes to Zn2 plus Cu. The ionic half equation. Don't be tempted to put in the nitrate. We all know that nitrate is NO3 1 minus, and that 3 is subscript, and the minus is superscript. But it doesn't ask for that, so we're not going to do that. The reactivity series can be written as a list of half ionic equations. These are all oxidations. Increasing strength of metal as a reducing agent. So something that more easily oxidizes is a better reducing agent. So the more reactive it is, the better reducing agent it is, because the more easily it oxidizes. So you're spinning a couple of plates in your brain on this one. Deduce which is the best oxidizing agent. So, which one is the best oxidizing? Well, this is the best reducing, the best oxidizing. It's going to be our copper, isn't it? 2 plus 5. But we'll accept copper as well. This is the best oxidizing. It's the best reducing. So this is the best oxidizing. Happy days. Give the ions in the list that can oxidize lead. Oh, well, this is reducing. This side's oxidizing. The lead's there. The one that's beneath the lead is again our copper. Copper. Oh, copper 2 plus. They seem quite happy with both of those. Copper 2 plus. Beautiful. Zinc is used in galvanizing as a method of rust prevention. Explain how galvanizing prevents rusting. So, first of all, the Zn acts as a coat or barrier. I'll give you one mark for a coat or a barrier. You can't see, the water can't see the iron behind it. Zinc. Okay. So this barrier stops the water and the oxygen reaching the iron. Very good. Whichever metal is under the zinc. Now, because zinc is more reactive than iron or steel, it will react first. Therefore, it prevents oxidation of the iron or steel. So it's sacrificial protection. You're sacrificing the zinc to protect the less reactive iron or steel, as well as the physical barrier in front of it. 3 marks? Yes, very good. 3 marks. One other method of rust prevention, don't forget, for rusting, you need oxygen and you need water, some iron, okay? You could grease the iron, or you could paint it, anything else? Or you could oil it, okay? Oil the metal to prevent the oxygen from getting to it. We then have a biology question, a nice little physics question, and our friend, the Haber process, always makes us happy. State the meaning of the term, of the symbol there. The symbol is clearly reversible reaction. It can go from reactants to products. In fact, it is going from reactants to products and from products back to reactants at equal rates. We call this at equilibrium. We'll accept at equilibrium. No, it wants to work reversible. Where does nitrogen come from? Nitrogen comes from the air. It's actually by fractional distillation of air to get nitrogen. And if you're lucky, you may well have had some nitrogen liquid and then put some organic matter into it and watch it shatter. into a million pieces. Hydrogen is from reforming steam, so you can say it's from steam or methane, natural gas. All are accepted as a source of hydrogen. The catalyst in the Haber process, don't mix up vanadium pentoxide, which is in the contact process. The Haber process is iron in the Haber process. Okay. Ammonia can be produced by a reaction involving ammonium salts. Here's some ammonium chloride, sodium hydroxide, forming ammonia. Don't confuse ammonia with ammonia. Ammonia is NH4 1+, Cl- in this case. NH3 is ammonia just NH3. What's the name of this type of reaction? Well, we are displacing. So it is a displacement reaction. Does that give me the mark? Yes, it is. Meiosis, mitosis. Aha! State the meaning of the term hydrocarbon now. This trips up so many students. Because many students will say, well, it contains carbon and hydrogen. And you know what? You're not wrong. But you'll get no marks for that. Because you have to put the word only. Okay? Hydrocarbon does not contain oxygen or nitrogen or sulfur or anything else. Only carbon and hydrogen. Without the word only, nil point, as they say en français. State the difference between the structures of alkanes and alkenes. Okay, so alkanes, these are saturated, related, and they have single bonds, 4 groups bonded, so carbon. Anything else that I wanted to say? Oh yeah, the general formula is CnH2n plus 2 subscripts. So the amount of hydrogen is double the amount of carbon plus 2 for an alkane, whereas for an alkene, the general formula is CnH2n, so it's double the amount, it's not double at 2, it's double the amount of hydrogen as there is carbon. And then we also say that it's unsaturated. It's null terms, meaning can you put more hydrogen into it. There is a double bond present and only 3 groups attached to each C. That's enough to hit the mark scheme? Yes, more than enough. Alkenes and smaller alkanes are made from longer chain alkanes by cracking, thermal decomposition. Complete the equation for the cracking of the alkane C20. So this is just about adding up. Okay, so we've got 20 here, carbons. Just look at the carbon. 20 carbons. 2 times 4 is 8 carbon. 2 times 2 is 4. 4 and 8 is 12. So this is going to make C8, isn't it? Yes, it is. And we do the same with H. I'll do the subscript in a minute. 42 here. I've got 2 times 8 is 16 there. 2 times 4 is 8. 8 and 16 is 24. So that's 18, isn't it? C8H18. You can see C8 is oct. And we can see twice 8 plus 2. 2 times 8 is 16. Plus 2 is 18. So this is an alkane. And the alkane is octane. Is that the mark? Yes, it is. Alkenes are more reactive than alkanes. They are. Alkenes are used in petrochemical industry to make a range of products. Dibromoethane is a pesticide. It is made by reacting ethene. This is ethene, CnH2n, C2H4, double the amount of hydrogen as there is carbon, with bromine. Complete the equation by drawing the molecular structure of dibromoethane. Now, I've not drawn this with this kit before. Let's have a look, see how we go. I want to see there. I want C there. I want H. I want H. Because H doesn't go anywhere, the H sits on it. And you can draw the bromines, which I'm going to do in a second, north or south of your drawing. I'm sure your drawing will be neater than Mr. Midgley's, and shapes, kind of line. Got our single bonds into here. Instead of having 3 areas of electron density, or 3 electron domains, is what I'm trying to say. 1, 2, 3, 1, 2, 3 for the alkene, 1, 2, 3, 4, 1, 2, 3, 4 for the alkane. So the drawing of the molecular structure of 1, 2 is actually 1, 2 dibromethane, because it could be 1, 1, lazy IGCSE. Okay, butene, 1, 2, 3, 4. My elephant parks backwards. Mostly eat purple biscuits, whichever way you want to remember it, just remember it. Butene reacts with steam to form butanol, right? The balanced symbol equation for this reaction. So we're going to have our butene, so that's butene to but is 4, and an alkene is double, not add 2, double, so it's C4H8 of the subscript shortly. We're going to add H2O, and we are going to make our butanol, which will be C4H9OH. Beautiful. Butene. Show my chemical symbols. Correct. Subscript H2O. This is one of the times when a computer is actually more laborious than writing in handwriting. But at least you can understand typing. Handwriting is nowhere near as neat as this. Alkenes can be converted into alkanes. They can, but why would you anyway? Well, the balanced symbol equation for the formation of ethane from ethene. So I'm going to have to do another C2H. How many H's? Double, right? 4 plus H2. Remember, do lots of subscripts again. It's going to go to C2. Now it's double, add 2, so it's C2 times 2 is 4 plus 2 is 6. So C2 is there. 4. The volume of the remaining gases is 125, so that's 50, I think there, isn't it? The carbon dioxide is removed. This leaves 25 cm cubed of unreacted oxygen. Determine the volume of oxygen used. Well, how can you get the volume of oxygen? So that's 175, 125, 50, so it's 50 away from there, and it's going to be 25, 175. The unreacted 25 from 175, that's going to be 150, isn't it? 150 cm cubed. The volume of carbon dioxide is going to be the 175 oxygen. Remaining gas is 125, so that's 50, 50. So that's going to be 100. Is my maths working? Yes, it is. 100 cm cubed. Deduce a possible formula for the hydrocarbon. Well, what could it be? It's burnt in 175 cm cubed of oxygen. The volume of the remaining gases is 125, so that's 50. Carbon dioxide is removed, it's the 25 of unreacted oxygen. The volume of oxygen was 150, that's 100. Carbon dioxide. If we have an alkene, so for instance, if we have, let's use a simple one, let's use C2H4 plus our 3O2, and that's going to make our 2CO2 plus 2H2 O, what can we see about the reacting ratio between the alkene and oxygen, and the amount or the moles is better of CO2 and H2O produced? One of these, okay. So one ethene and 3 oxygens makes 2 CO2, so it's a 3 to 2. So this is in a 3 to 2 ratio. There's 3 50s here and there are 2 50s there. So that's going to tell me that's going to be an alkene. So you can actually have any alkene. I'm going to choose this one. I'm going to call it that. It's going to be an alkene. An alkane will have a different ratio of carbon dioxide to oxygen. Write a balanced equation for the reaction of this hydrocarbon with oxygen. Well, I'm just going to, so given the formula, and just got ahead of myself, there we go. Suggest a possible formula. Butene, you have propene, butene, pentene, hexene, heptene, octene, nonene, decene, undecene, dodecene, and so on. Increased concentrations of CO2 in the atmosphere contribute to climate change. Feel better. State the general name of gases like carbon dioxide that contribute to climate change. I think we're going to look at here. Greenhouse gases. Have they added anything else creative? No, they haven't. Give the name of one other gas that contributes to climate change. Let's have methane. Not just the exhaust from windbag politicians. Fertilizers. This is biology, bacteria, oxygen, a bit of physics. I think we've done physics. Yes, I think we've done for this little video on how to answer IGCSE 0654 coordinated science questions for chemistry. I hope you found that little discussion and work through useful. Don't forget, comment, like, subscribe at the bottom of this video. Thank you very much for watching. Have a great day.